According to the CDC, there's more than 40,000 births per year that are affected by congenital heart defects. These are defects that infants are born with, which motivates a lot of research into this area. Hence why the International PC4 database was created, in order to collect CHD patients' data and use it for research. However, the data collection process can be very tedious. Say you have this clinical note and you want to extract these pieces of information from the note. Say it takes you around 10 minutes. Say you have more than 6,000 notes a year. That's going to take you more than 1,000 hours per year, which is very time-consuming for nurses, which is a problem that Texas Children's Hospital has. Hence why we're collaborating with them to develop an NLP algorithm that can expedite the process of uploading the data into PC4. That can allow us to do more than 6,000 notes in less than 2 hours. That can greatly decrease the amount of time nurses have to spend on the computer and greatly increase the amount of time they're able to support patients.
There are a total of 9 different entities that we have been tasked with extracting. These entities fall into 3 different categories: numerical data such as birth weight or birth length, Boolean data such as whether or not a patient was born prematurely, and description type data such as what chromosomal abnormalities a patient might have. This now brings us to the data pre-processing step in our data pipeline. Many patients have multiple hospital visits over many years, with a new clinical note created for each visit. Medical record numbers, or MRNs, are the only unique patient identifier that remains constant across multiple hospital visits. The very first step of our data pre-processing is to sort all of the clinical notes by MRN and combine them into one singular text for each patient.
So we have 2 ways of taking the data that we're given and actually putting it in a form that's useful for us in training. The first way is using our database data and looking for specific points for a patient and trying to find those points within a clinical note. For example, here we have 39, so we look through the note for that. We can then extract the indices and put it in a form that's usable for us in training. We also do rule-based NER, where we look for common abbreviations or typos for the different fields, and we then try to find that within the clinical note. After we have found that specific string, we can then find a numerical value that occurs after it and extract the indices in the same way.
Once pre-processing is complete, the next step of our data science pipeline is modeling or extracting the named entities. And to do this, we use a Python library known as spaCy, which is a state-of-the-art NLP framework. Our spaCy model takes in labeled training data, as shown on the left, and uses a transformer to create word embedding vectors. Then, the NER step learns the weights of a neural network, which uses LSTM, long short-term memory cells, in order to preserve meaning across sentences and paragraphs. In order to improve the performance of our NER model, we added a rule-based component built into spaCy between our transformer and our NER steps. The rule-based NER uses regex matching on all of the syndromes, chromosomal abnormalities, and non-cardiac abnormalities listed in the PC4 manual in order to label any low-hanging fruit before it proceeds to learn the neural network to complete the NER model.
The next step was to evaluate model performance. We used recall to evaluate the individual PC4 entries, which is a metric that emphasizes accuracy relative to the number of false negatives. For our data, a false negative is an entity in a clinical note that we failed to tag. This is a major issue, which is why we chose this metric. And displayed here are our results from last semester, sorted by descending recall. The overall recall was around 46%. And here are our results from this semester, concatenated. Green means the recall went up, and red means it went down. The overall recall rose to 52%, and we can see that this is largely thanks to the significantly improved recall for birth length, syndromes, and non-cardiac abnormalities. Decreased recalls are due in part to the non-deterministic nature of the neural network training. Overall, these improvements were obtained by incorporating spaCy's built-in rule-based NER, as well as label mapping improvements, as discussed earlier.
This semester, we have started exploration of BioBird and an alternative to spaCy. BIRD, in general, is a transformer-based network which uses attention. It means that it determines meaning of the word based on the meaning of other words in a sentence. BioBird is a special case of BIRD which uses biomedical data to be trained. Later, after we take our trained model, we copy the weights and create vectors of length of more than 700 entries for each sentence and word in the actual data we want to perform named entity recognition of. We take these vectors and we write a neural network which does named entity recognition of this data set. An advantage of using BIRD over spaCy is that this model is easily tunable and it's easily changeable, while spaCy has a lot of secrets and it's not even known what the exact architecture of the model is.